Welcome back to the Ephemeris podcast. I'm your host, Aphelion, and it is nice to be back for another episode in another week of this year. And it is coming to a close, which is pretty wild because I think the end of the year will also be signifying the end of the season. And next year, we're going to get into some new stuff, I should say. I've mentioned quite a few times before that I think with season three we're gonna transition into more novel stories, or I guess breaking stories in the field of astronomy. And so once we're done with Einstein and I think one or two more people like Carl Sagan, we will move into that realm of astronomy and move into a new season. So that's all fun, but hey, for that matter, the wait is finally over. We are talking about Albert Einstein. And the attempt here is to encapsulate all of his work, which there is like a ton, in the most concise manner. I'm going to mention a couple of like not so astronomy related stuff in the episode, but for the most part, we're going to keep it with, special relativity, general relativity, and stuff like that, which is going to relate to space science. So, let's start with the life of Einstein. Albert Einstein was born in Ulm, Germany in 1879. His Jewish parents moved to Munich in 1880, where Einstein stayed and went to school despite his parents going to different places. But then in 1894, he was like, all right, I'm going to move to Pavia, Italy. As for Einstein's genius early on, as we know, he was a quite an intellectual throughout his life. He was learning calculus, algebra, and Euclidean geometry when he was only 12. And he had learned integral and differential calculus when he was only 14, which is wow. I mean, if I'd learned the second and third parts of calculus at that age, God knows where I'd be. So that's quite a feat. And at 17, Einstein enrolled in four-year mathematics and physics teaching diploma at the Federal Polytechnic School, which I don't think I'll really understand. Wanting to get a teaching diploma program that early, I mean, man, that is something. And he's like living the life, or he's living life the way that, STEM majors watch their YouTube videos, like 2 times speed, quite literally. So, Einstein also met his first wife, Mileva Maric, at the Polytechnic School, who may or may not have contributed to the Annus Mirabilis papers, which we will talk about in a minute. And as for the rest of his life, he gets into like a series of relationships. We're not going to quite talk about all of that. In other news, though, Einstein published his first work in 1900, where he proposed a model of intermolecular attraction that he afterwards disavowed as worthless. So I think that's, a good precedent to say, you know what, let's leave that aside. Einstein completed his doctorate dissertation in 1905 titled A New Determination of Molecular Dimensions, and then came the Annus Mirabilis papers. And the rest of his life is relatively well known from there. He took on a bunch of like teaching and university positions in the 1920s and 30s. He spent a lot of time in foreign countries, especially the United States, where he emigrated to in 1933, and he gained permanent residency in 1935. Einstein also got involved in the Manhattan Project, which, I mean, I'm assuming most people know about due to the movie Oppenheimer. And so, after that whole situation, there's a less talked about part of Einstein's life, and that is his involvement with the NAACP, Lincoln University, which is a historically black college in America, and sort of giving speeches on racism and, issues with racism. So I thought that was interesting as well. I think the there are like some excerpts or quotes online that describe that, Einstein, having faced discrimination as a Jew, also stood up for the rights of African Americans at the time. So yeah, that's all good. And so with that all talked about, let's get into the works of Einstein. So I mentioned Einstein's dissertation at first, so I'll give you the provided summary of the work here. Quote, "It will be shown in this paper that the size of molecules of substances dissolved in an undissociated dilute solution," which an undissociated solution you can basically think of as non-ionic compounds or solutions of them. So the size of molecules of substance dissolved in this can be determined from the internal viscosity of the solution. So just think like, how fluid is a solution? Is it like runny? Is it thick, kind of thing? If you've learned about viscosity in chemistry, you'll kind of get the idea of what I'm talking about there. So yeah, it can be determined from the internal viscosity of the solution and of the pure solvent, and from the diffusion rate of the solute. So how quickly the solute is dissipating in the solvent, provided that the volume of a solute molecule is large compared to the volume of a solvent molecule. So you think like a liter of water versus, I don't know, 5 grams of salt, something like that. This is possible because with respect to its mobility within the solvent and its effect on the viscosity of the latter, such a molecule will behave approximately like a solid body suspended in a solvent. So yeah, basically it's just saying like, because we've got this undissociable solution and we're putting this substance in it, it's basically going to change how fluid the solution is, and based on that and the fact that the solute is much smaller than the solvent in terms of how much there actually is, you can kind of treat it as like there's just solids suspended in this solvent, and the amount of volume that it takes up in that way will help you decipher the size of the molecules of the actual substance. So yeah, obviously this is a more so like chemistry kind of thing, but I think it's quite cool nonetheless. It's very important when we talk about Einstein's work in statistical mechanics, and so yeah, just cool little work to mention. Then there are the Miracle Year papers and the Annus Mirabilis papers, just to be clear, because there are two ways of referencing. There's the Latin way and the English translation of that Latin name. So there are 4 of these Miracle Year papers. I will refer to these papers as the Miracle Year papers from now on. So the first of these papers is on the photoelectric effect. The second one is on Brownian motion. The third one is on special relativity. And the fourth one is on the world-famous matter-energy equivalence. So, let us start with the first work, which is titled "On a Heuristic Viewpoint Concerning the Production and Transformation of Light and the Discovery of the Photoelectric Effect." So, in this work, the main thing that Albert Einstein discusses is the idea of energy quanta. He says that energy is not spread to the spaces that light goes to, but that light contains an energy that travels a distance before it undergoes some other transformation. Or at least, this is the idea. And so what did this lead to? The theory that energy comes in discrete packets and is not simply distributed everywhere, especially in terms of, light and electromagnetic radiation. What does that mean for space science? That means that this principle can be applied to black bodies, which absorb all electromagnetic radiation. So the discrete packets is essentially what energy quanta describes, and this contradicted some of Maxwell's theories about light. And to show this, Einstein used the example of a cathode ray. And he says, quote, According to the view that the incident light consists of energy quanta, the production of cathode rays by light can be conceived in the following way. The body's surface layer is penetrated by energy quanta whose energy is converted, at least partially, into kinetic energy of the electrons. The simplest conception is that a light quantum transfers its entire energy to a single electron. And if you can imagine the energy transfer that is happening in what Einstein is describing here, you get a really nice visualization of the photoelectric effect. And this is where the idea of E equals to HF comes from. I don't know if the symbol is actually H or if it's pronounced a little differently, but the symbol looks like an H, so I'm going with that. So that's the photoelectric effect. Let's talk about the second piece, and this is titled On the Motion of Small Particles Suspended in a Stationary Liquid, and this will obviously have to do with Brownian motion. I'm going to be very brief on this one because, again, it's not too space sciencey, but it's still cool. So at the time, atoms weren't set in stone as necessary in the field of science, or like with the theories that were out there. But there was work done by scientists like Robert Brown and John Dalton, which were making it inevitable that the atom would be widely accepted. And as I mentioned before, Einstein did some work on statistical mechanics, and this is where he puts that to good use and proves that the atom is undeniably real. He used the kinetic theory of gases to assert that atoms must exist for Brownian motion and displacements of particles to occur in a suspended medium. So, yeah, just a quick word on that there. It is important because obviously, we understand now that the most basic form of matter is the atom. And, we do quite a lot, or we use that, the idea of atoms quite a lot in chemistry, sometimes physics when, you're considering like electromagnetism and stuff like that. So, yeah. That is the second work. The third work is titled On the Electrodynamics of Moving Bodies, and this is where the fun begins. We start off this work with Einstein mentioning his concerns over Maxwell's theories on electrodynamics, then stating, quote, "The same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. We will raise this conjecture, which will hereafter be called the principle of relativity, to the status of a postulate, and also introduce another postulate which is only apparently irreconcilable with the former, namely that light is always propagated in empty space with a definite velocity c, which is independent of the state of motion of the emitting body." So these are some very, very, very important ideas, like two principles of relativity, which is going to open up the door to a lot more theories and a lot more important work. In fact, this work is going to open up the matter-energy equivalence and the famous law E equals to mc squared. So there's the foundation that we need for that. And in this work, Einstein also discusses time in a way that can be appreciated not only because it's not necessarily scientifically profound, but I find it philosophically thought-provoking. So he explains that time is not concrete. We perceive time as the connection between a certain occurrence and, say the positions of the hands on a clock. Which is, I don't know, I took this idea in the direction of, like, what is time? Like, that part of the work kind of made me think about that, and to me that makes this deep more than anything. But obviously Einstein he's just making it clear that like what he means by time, because with relativity it's important to be very, very precise in your definition of time. So yeah, that's what his purpose was. The way I see it, it sounds like a really philosophically thought-provoking idea. So Einstein here also establishes that time is not common, that the time in which something occurs is not the same for two different remote locations unless the speed of light is equal going both ways. So uh, a light ray that travels from A to B must travel from B to A in the same time. And he uses this idea to derive an equation that calculates the speed of light in a vacuum. And from there, Einstein uses a ton of mathematics to analyze the electrodynamics of a vacuum, or the electrodynamics in a vacuum during motion, And he investigates the mass of a slowly accelerated electron in such an environment and determines the kinetic energy of the particle. And I think you'll see where this is going. As the electron is to be slowly accelerated, quote, and consequently may not give off any energy in the form of radiation, the energy withdrawn from the electrostatic field must be put down as equal to the energy of motion, W, of the electron. And he goes on to define W as mc squared times 1 over the square root of 1 minus v squared over c squared, all of that minus 1. And determines velocities beyond the speed of light impossible. So yeah, that is the third work. Now we obviously have the appearance of mc squared here, but it's not exactly the mass energy equivalence. So the last of the Miracle Year papers is pretty much designed to do that, and it's titled, Does the Inertia of a Body Depend on Its Energy Content? Where he derives the actual equation where it's like E equals to mc squared, period. And so if a body gives off the energy L in the form of radiation, its mass diminishes by L divided by c squared. And so the fact that the energy withdrawn from the body becomes energy of radiation evidently makes no difference. So we are led to a more general conclusion that the mass of a body is a measure of its energy content. If the energy changes by L, the mass changes in the same sense by L divided by 9 times 10 to the power of 20. And yeah, so basically the mass energy equivalence is going to become really, really helpful for nuclear reactions because, as I mentioned, this whole process of like emitting energy in the form of radiation, losing mass, and general conclusions based on that. So those are the Miracle Year papers, but there is still more. Einstein gets into his theory of general relativity, not special relativity, just to be clear, between 1907 and 1915. Or do I have that flipped? I can't remember. I've written general relativity, but it could be special. I think it's special, but it's, yeah. Let's move on. On the relativity principle and the conclusions drawn from it, Einstein explains the equivalence principle. What the equivalence principle means is it basically just equates inertial mass and gravity in terms of, general relativity or special. Darn. I'm thinking general relativity at this point because I don't think I would have made the same mistake twice. So I think it is actually general relativity. So anyways, what does the equivalence principle mean? The equivalence principle basically says that if you were in free fall, it would be the same as you feeling weightless and not accelerating anywhere. So really, you are not accelerating due to gravity. But how is that possible? Because in later works, this idea will arise that gravity is simply the result of the curvature of space-time. And that might sound really, really complicated, but if you've ever seen like people do like models of just like what it would look like for certain masses to curve space-time, then you'll understand that like if you imagine yourself like relative to sort of a field of space-time around you and you're standing on the earth, sort of earth, the sort of phenomenon of earth pulling you when you jump is just going to look like you falling into this bend of space-time if you kind of just like um, see it from a huge retrospect and in terms of, Earth actually curving space-time. So yeah, that might have sounded really confusing, but general idea is that gravity is simply the result of the curvature of space-time. And this idea is actually put perfectly by John Archibald Wheeler, who says, quote, "Space-time tells matter how to move, matter tells space-time how to curve." So maybe that's a better explanation than the one that I gave. I'm not to decide. Einstein, in his relativity principle piece, also talks about gravitational time dilation, which is the slowing down of time as you get closer to something with a strong gravitation, like a black hole. Einstein also talks about gravitational redshift, which is the energy of light kind of decreasing after traveling out of a gravitational well. And black holes will agree with this idea. If you've seen any images of black holes are like, kind of the vicinity around a black hole in an image, you'll know that it tends to be quite like, a lot of warm colors. I think it tends to be orange from what I can remember. And stars near to a black hole appear redder. So, yeah, that's kind of an example where this would apply. And the last of Einstein's ideas in this piece is gravitational lensing, which is the bending of light as it passes some matter to reach an observer. And so the next piece, which kind of follows up a little bit on these ideas, it's titled "On the Influence of Gravitation on the Propagation of Light," where he states, quote, "Light rays passing close to the sun are deflected by its gravitational field so that the apparent angular distance between the sun and a visible fixed star near to it is increased by nearly a second of arc." And guess who went on to prove this true? Yes, Arthur Eddington, Sir Arthur Eddington. In 1916, Einstein predicted gravitational waves to be ripples in spacetime, and he was not the first to predict gravitational waves themselves, but the first to propose that they are ripples in spacetime, and sort of this idea of gravitational radiation using Lorentz invariance. And Lorentz invariance represents Lorentz scalars, which are expressions that produce scalar values that don't change under any 6-parameter linear transformation. So basically a sprinkle of vector calculus to figure out, gravity also has its own radiation, or can create its own radiation. So later on, Einstein applied some of the above ideas to cosmology. He discovered that the general field equations predicted a universe that was dynamic, either contracting or expanding. Now, he didn't have the experimental or observational means to prove this, so he introduced a cosmological constant to maintain a static universe theory, and so that is known as Einstein's static universe. But if you'll remember, there's somebody who did cosmological constants better than anybody else, and that was Edwin Hubble. And so with Edwin Hubble's work and Einstein figuring out, he was like, oh, wait, you know what? It doesn't have to be static after all. So he created a new theory, which is known as the Friedmann-Einstein universe. And the main thing you need to know about this theory is literally that it's possible for the universe to expand and contract without a cosmological constant, keeping it static. And so that's pretty much all. There's also the Einstein de Sitter universe theory, but it's not, too out of this world. So we're going to leave that be. And so this is pretty much the bulk of Einstein's significant work. Now, later on, Einstein will work on a unified field theory, which kind of tries to combine magnetic, and gravitational forces into a single field. And so this is basically Einstein's theory of everything minus the constants of nature and fields existing by nature. And it might seem as though with this theory, Einstein was interested in putting together all parts of physics, but he was not quite fond of quantum physics and mechanics beyond his work in 1905 with the photoelectric effect. So, yeah, that kind of translates because Einstein didn't really have strong or weak forces included in his unified field theory. So, that is all for Einstein's work that we will be discussing today, at least. He received the Nobel Prize of 1921 in 1922 because of some special circumstances. But, anyways, he received it for his discovery of the photoelectric effect specifically. And yeah, that is all that there is to this episode about Albert Einstein. If you all enjoyed listening to this podcast episode, I would sincerely appreciate a follow on Spotify if you're listening on Spotify, and a subscribe on YouTube if you are listening there. And until the next episode, I will see you all later. Peace.